What I would like to do now is start talking about three groups of mammals. In particular, I want to talk about the rodents and lagomorphs, and I'm going to consider those together in the same group, and there's a reason for doing that. And then I'd also like to talk about the carnivores and the cetaceans, not necessarily in that order. In this presentation, I'm going to talk just about the rodents and lagomorphs. And the reason for talking about these guys is that they are perhaps the most successful of all um, mammal groups, with the exception, obviously, of the bats. The bats are clearly the most successful. So let's take a look at these guys. There are a bunch of families and a bunch of genera, overall something like almost 1,700 species, and that number increases almost every year, and that's primarily a consequence of new discoveries in South America. But they occur across the globe, everywhere except for Antarctica, and I'm sure if we ever have the ability to find fossils or to search for fossils in Antarctica, I'm sure that we will find them there as well. One of the reasons why the rodents and lagomorphs are so interesting is because of the morphological diversity that exists within those groups. And at the same time, that makes it sort of difficult to figure out what the true taxonomic relationships are amongst all of the different groups. If you're relying on genetic techniques, that is a help, but it is confusing, to say the least. And while the rodents have had such enormous evolutionary success, the opposite is true for the lagomorphs. So they've not been a particularly successful group. Even if you think about the state of Missouri, you just have a few species of lagomorphs. You have swamp rabbits and then eastern cottontails, and then on the one extreme corner of the state, you have sometimes jackrabbits, but not nearly the sort of diversity that you get with rodents. So obviously one question is, why is that so? Why has one group been so successful and the other not? And that's the question that I want to address in this particular lecture. Whereas you have this huge number of species in the rodents, you only have about 63 species of rabbits, or hares and rabbits, lagomorphs across the globe. So they don't have a worldwide distribution, or they didn't initially at least. They were introduced to Australia, and they were introduced to the southern portion of South America. But of course the question is then, why do we consider these two guys together? And it turns out, in fact, that the Russians consider them as to be all part of one group. It's we, the Americans, that have separated them. And we have a tendency to poo-poo what the Russians are doing, or to laugh at what they're doing. But it turns out that there is some solid reasoning behind what they're doing. And as a matter of fact, there's this gentleman by the name of Stuart Landry. He's at the State University of New York, and also does a fair bit of work, or used to do a fair bit of work, at the American Museum. And what he did was find this sort of interesting relationship between these two groups that we've overlooked for a long time. Stuart Landry is, by the way, just as sort of an aside, is an old school kind of a fellow. I remember back in the day when people started moving to slides from overheads at scientific meetings. He was still using overhead transparencies. And when the whole rest of the world was going to PowerPoint presentations, he was still using overhead transparencies. And the last talk he gave that I saw, which was probably about 10 years ago, he was still using overhead transparencies rather than slides. So he did not go into the 21st century with ease. He's definitely an old school kind of a fellow. But at any rate, so what is it that sort of links these two groups? And the one key characteristic that most people miss when they're looking at skulls is what's happening with the pterygoid process. And it's reasonable that that should be the case, because in most museum specimens, if you turn it over and look at the pterygoid processes, in most skulls, those processes have been broken off. That's certainly true for all the skulls that we have in the lab, in the comparative anatomy lab where we're taking this course. Most of the most of those pterygoid processes are broken, and they're fragile. What are they used for? Well, they are the point of origin for the pterygoideus muscles, which go from those pterygoid processes down to the angular process on the medial surface of the dentary bone. But if you look at a rodent, what you discover is that those pterygoid processes go all the way back and almost touch the auditory bullae. And you can see that here on this particular skull. There's one pterygoid process right there, and there's the auditory bulla. There's the tip of the other pterygoid process, and there's the auditory bulla. And in both cases, these processes almost touch those auditory bullae. This, by the way, is Anomaloris derbianus, which is Lord Derby's anomaler. It's one of the African scaly-tailed flying squirrels. It's not a squirrel, but it does glide. And it's notable because of the dentition, and if you look at those teeth, it's a very characteristic sort of tooth, and that's one of the features that sets the anomalures apart. At any rate, these pterygoid processes in rodents almost touch the auditory bullae. There is only one other group of mammals where that's true, and that's in the lagomorphs. And in the lagomorphs, the same condition persists. All right, so that is clearly, I think, an important similarity between these two groups. It's not found anywhere else. Okay, and I think that's probably good reason for thinking that these two groups might be related. And of course, there are other features that we'll talk about in a little bit. All right, so let's begin then by looking at the rodents, and what I want to do is divide them up into three major groups, and the groups that I'm going to divide them into are based on the morphology of the jaws, and the morphology of the masseter muscles, and then secondarily on the morphology of the jaw. So when we do that, we can think of rodents as being either sauromorph, myomorph, or hystricomorphous. Sauromorphous rodents are rodents that have a squirrel morphology. Myomorph rodents are rodents that have a mouse morphology, and hystricomorph rodents are rodents that have a porcupine kind of morphology. And as a matter of fact, at one time early on when we were constructing phylogenetic trees for the rodents, these were actually considered as groups or real taxonomic units, taxonomic divisions within the rodents. That's no longer true. It turns out that they're not all that useful in a taxonomic sense, but it does help us understand what's going on with the masseter muscles, and the whole success story of the rodents and the lagomorphs comes down to what's going on with the masseter muscles. So those are we've talked at some length about the temporalis muscle when we were doing our geometric morphometrics with the jaws early on in the semester. We talked about the importance of the temporalis muscle. The other muscles that are operating on the jaw are the masseters. There's a superficial masseter, a medial masseter, and then a deep masseter. And it's how those muscles are organized that helps us distinguish between these different groups of rodents. All right, so a little bit more about that in just a few moments. I'm going to skip all of this business about the teeth and all the uniqueness about the teeth, other than to point out that amongst rodents, and this is true for lagomorphs as well, that there are no canine teeth. So if you look at the dental formula, and I know we haven't talked about dental formulas, but if you look at the formula that's given here, 1/1, 0/0, 2/1, and then 3/3, that refers to one side, either the left or right. It doesn't make any difference. The upper number refers to the upper jaw, and the lower number refers to the lower jaw. So in this case, there's one upper incisor and one lower incisor. And then for rodents, there are zero upper canines and zero lower canines. And then there's two upper premolars, one lower premolar, and then three upper molars and three lower molars. And if you add all of that up across both sides, you end up with 22 teeth. Here is one difference between rodents and lagomorphs. In lagomorphs, the number of incisors is different. Okay, they have this little peg-like tooth behind one of the upper incisors. And of course, there is another important difference here too, not between rodents and lagomorphs, but between rodents, lagomorphs, and all other mammals. And that is that these incisors are open-rooted, that is, they grow continuously, and they tend to have a very hard anterior surface that contains a lot of iron. And obviously what's happening is when the lower teeth and upper teeth occlude, when they come together, they are actually sharpening, the lower teeth are sharpening the upper teeth, and then the upper teeth are sharpening the lower teeth, so that you always have this very sharp knife-like surface on the tip of the incisor. And one of the ways that's maintained is by the fact that the anterior surface of that tooth is covered with iron. And it obviously then doesn't wear nearly as quickly. So these teeth are open-rooted, which means they grow continuously throughout life. That's true in other animals as well, horses, for example, or deer, right? So in other animals, you see the same sort of pattern, but they don't have the iron content on the anterior surface of the tooth. So here, let's look at this little diagram. The lower incisor is open-rooted, and here you can see how that root works out. Right, it's going across the entire length of the horizontal ramus and actually up into the right beneath the masseteric fossa, and then the upper tooth is sort of curved as well, so they grow continuously. One interesting aspect of this, and this is important, there are really two things that I want to point out here. The first is, if you were to think about this tooth and think about when this animal is closing that jaw, where are the stresses that are being imparted to the jaw? Where do they manifest themselves on this tooth? And the answer is that there are these little microfilaments in a crosshatch pattern that surround the alveolus and attach themselves to the tooth. So when the tooth bites down, it's not really experiencing shear forces like you would imagine. Instead, because this tooth is curved like that, it's actually being compressed and shoved back into the alveolus. But it's these cross-hatched microfilaments that are absorbing that tension and hold the tooth into place. And it is for that reason that an animal like a beaver can have such a powerful bite and actually use its teeth to fell a tree. On the upper side, what I want to draw your attention to is the fact that here's the tooth coming up like this, right? It curves around, so it's the same sort of pattern. But notice what happens here with this suture. So this is all the premaxilla right here, the premaxillary bone. And notice that there's this suture and how the suture curves around like that. And there's a reason why it curves around. In most other mammals, it doesn't do that, right? But here it curves, and what that does is it increases the length of that suture. And as you know, the weakest part of any construction is where the joint occurs. So the weakest part of the skull, especially if this animal is going to be imparting a lot of force to those anterior incisors, this is the weakest part. The fact that it curves around and it's longer means that it's actually going to be a stronger joint than if it were just to be a straight line. So this is a little evolutionary trick that the animal has used to strengthen that front part of the skull and therefore allow the animal to impart greater force to those anterior incisors. All right. I'm going to skip over a lot of this stuff. The only point that I want to make is that the teeth in rodents are extremely complex, and they are related to the sorts of diets. So you can look at the morphology of these teeth, and you'll find all sorts of bizarre patterns. And these are teeth that are designed to do different sorts of things. And the list here is a naked mole rat, a murid rodent, which is an old world rodent, porcupines, chinchillas, a different kind of a rodent, a murid rodent, old world rodent, and then yet another kind of old world rodent. So the morphology of these teeth is quite dynamic and is one of the reasons why the group has been so successful. All right, so there is something else that I want to point out to you, and that has to do, if I can get to that point, that has to do with how this lower jaw is being used. So here, let's look at our different kinds of rodent skulls. And we talked about cyuromorph, myomorph, and hystricomorph. And if you look at this illustration on the right-hand side, I have some arrows drawn in there, which shows you what's happening with the muscles that are the superficial and deep masseters that are controlling the lower jaw. So first, two things. Number one, there is actually yet a fourth kind of skull that we can define, and that's called the protrogomorph. That is presumably the ancient or the primitive condition of the rodent skull. The other thing that and that's illustrated at the top. The other thing that I want to point out is that the two dentary bones, right? The jaw is made up of two dentaries, one on the left, one on the right. There is a symphysis between them. That symphysis does not fuse. So it's just like in human females where the pubic symphysis does not fuse, at least not until much later in life after childbearing. And what that means is there's some movement there between those two dentary bones. And what that enables the animal to do is to manipulate the two dentary bones independently. So what the left dentary is doing is not constrained by what's going on with the right dentary. And in fact, what that enables the animal to do is to use the lower incisors almost as a pair of tweezers, so it can spread the tips apart and then bring them back together. One jaw can go up a little bit while the other one is going down a little bit. The animal has a lot of control over those two dentary bones. It's not like us where that dental symphysis is fused. We have no independent mobility left to right. So let's look now at what's going on with these three different morphologies here for the masseter muscles. We're going to ignore what's going on with the primitive condition. The first one is the cyuromorph, and notice what happens there. There's one of the masseters, the deep masseter, which is going from the horizontal ramus and then going up to the side of the skull, underneath, either attaching to the zygomatic arch or going underneath the zygomatic arch. The superficial masseter, however, is going from that angular process, and there's a groove right in front of the zygomatic arch, and this is a groove that's pretty large. You could lay a pencil in there, or if this is a bigger animal like a marmot or something like that, you could actually lay your finger in there. So it's a nice thick groove. And if you look at this, you'll realize that what's happening is that one masseter is going from anterior to posterior, and the other masseter is going from posterior to anterior. So they cross each other. And what that means is the animal can take this jaw, move it forward, move it back, manipulate it side to side. Now compare that with what happens in the myomorph form, so the mouse-like skull. And now, once again, you have one masseter muscle, which is going from the angular process up towards the front. And now you have a second, which is going from the horizontal ramus, goes up underneath the zygomatic arch, and then goes through this foramen, right? That's not the eye socket that it's going through. It's going underneath the eye and going through this infraorbital foramen to attach to the rostrum. All right, so now the muscle actions are a little bit different. If you look at the hystricomorph condition down below, right, now what you see is that you have one masseter which is going anterior to, or rather posterior to anterior. The second one is going posterior to anterior, so they're both going in the same directions, but they're operating on slightly different angles laterally from side to side. And notice now as well what's happened to the infraorbital foramen. It is absolutely huge, which means, of course, that the size of the muscle that can be going through there is quite large. And that muscle, too, is going to attach to the side of the rostrum. All right, so here's just another illustration of what's going on with the muscles, right? The medial, the lateral, and the superficial. Masseter muscles, we're going to skip right past that. And we can look at a bunch of examples. So for the most part, those sorts of classifications are pretty straightforward. There is, however, one example where it gets a little bit confusing, and that happens with the Anomaluridae. I've talked about the Anomalurids before, and that's primarily because they are this weird group of African rodents that most of them are gliders. There are only a handful of species. There is, however, one species which does not glide within this family, so it's a really small family. It's poorly known. And if you look at these guys, some people classify them as Sauromorphous, others classify them as Hystricomorphous. So it's kind of weird. Okay, there's something odd going on with this muscular anatomy on the Anomalurids. Okay, so all of these different morphologies represent solutions to the problems that are posed by herbivory. Okay, so we've been talking about Sauromorphous, Hystricomorphous, and myomorphous rodents, and about how that relates to morphology of the masseter muscles. There is yet another component to this, and that's what's going on with the lower jaw. And while Sauromorphous, Hystricomorphous, and myomorphous skulls don't align with any sort of phylogeny that makes sense, it turns out that the jaws do. So we can look at all rodents and we can classify them as either Saurognathous or Hystricognathous, that is, squirrel-like jaws or porcupine-like jaws. So let's look at those two jaw morphologies. Let's look at the diagram down below here. And if you look at both A and C, figures A and C, what you notice is, if you were to draw a line from the incisors back to the mandibular condyle, almost everything falls underneath that line. So the horizontal ramus and the vertical ramus all fall in line there. And also the cornoid process and the angular process are all basically in the same plane. On the other hand, if you do that in figures B and D, what you'll notice is the angular process flares out dramatically to one side, so that now that vertical ramus is no longer in one plane, it's actually now cupped. And obviously what's going on there is that you've increased the amount of surface area for insertion of the masseter muscles onto that angular process. So this kind of morphology is going to be one that is able to generate a great deal of force compared to what's happening with the other. Well, the first is Saurognathous, the squirrel-like. So A and C are squirrel-like jaws, and then B and D are Hystricognathous, that is porcupine-like jaws. And here you can see sort of an extreme example of that. So this truly is a bizarre jaw. This is for the nutria. Myocastor coipu, nutrias are not endemic to Missouri. They were introduced into the U.S., and that's sort of an interesting situation in and of itself. We have a number of nutria in the collection, and most of them were collected just south of Cape, right off Highway 25. There's a culvert which goes underneath Highway 25, where Penzel Construction used to have a yard right there, and I think now there's a sheet metal recycling place or something there. But that's where we've caught most of those animals. Notice what happens with the angular process here. It just flares out dramatically to one side, and it has this kind of hourglass figure to it. And you don't get the same kind of curvature in the alveolus for the lower incisor either. But nutria were introduced into this country from South America, so it's a South American rodent. And the reason it was introduced was because of the fur trade. The reason St. Louis was started as a town, and one of the reasons why Cape Girardeau is on the map, is because it was a stopping point for river traffic up to St. Louis, and most of that river traffic involved the transfer of pelts and so on. So St. Louis was a fur trading capital. And the reason for that is that many beaver were harvested in this part of the country, and most of those beavers found their pelts on the way to France, where the market for beaver pelts was huge. And of course, at some point, it became difficult to supply the French market with sufficient quantities of beaver pelts. So people started farming in Louisiana. They started farming nutria. So they had trapped nutria down in South America, and they began raising nutria in Louisiana. And not surprisingly, the nutria got out, right? They escaped and have since expanded their range throughout much of the southeastern United States, especially in places that are swamp-like or have lowland kinds of habitats. So it is an invasive species. It is a pest species, not to the same extent as feral hogs, but it is a pest species. They are cool, though. They have really interesting looking skulls and jaws. What's sort of sad is the fact that the French couldn't tell the difference between a beaver pelt and a nutria pelt, which leads you to question their state of mind, I suppose. It's pretty easy to tell the difference. A beaver pelt can be quite luxurious. Nutria pelts, not so much. There are just a couple of rodents that I want to talk about and draw your attention to, just because they are so bizarre. One of them is Aplodontia rufa, and this is oftentimes considered to be sort of a primordial rodent. The common name is the mountain beaver. It's not a beaver, and I suppose it does occupy, or it does occur in mountains under some conditions, right? But there is a population of Aplodontia on the California coast, and there aren't any mountains there in Central California on the coast other than the coastal range, which is somewhat inland. Okay, but these guys are kind of cool. First of all, you notice what's happening with the external auditory meatus, right? It's just this sort of broad structure which extends out to the sides. The other cool thing, though, is when you look at the cheek teeth, the premolars and the molars. And there you'll notice that they have this weird little flange which goes off to one side. It's the only rodent that does that. And I'm fortunate in that I have the lower jaw of one of these animals. It's the only aplodont that I have in the collection. And it's a perfect foil for students in mammalogy when they take their practical on the rodents. All right, so there's the anterior part of the dorsal view of the skull. Right, so it's again that sort of hourglass shape, these very broad zygomatic processes, which isn't atypical of rodents, I suppose, but it is not common either. And here you can see what those little projections, those lingual projections, are on the teeth. let's consider just for a moment what's happened with rodents in South America. And South America is the sort of gold mine for small mammal biology. New species are being discovered every year. It's just a large number of new species. Let's just look at a couple of arboreal species. And these are both squirrels, right? So the family Sciuridae did make it to South America. And you see this beautiful diversity in color patterns. These illustrations come from John Eisenberg's volume on the mammals of his 3-volume set, or 2-volume set on the mammals of South America, or the mammals of the neotropics, I should say. But this incredible diversity of color patterns, and it extends, not just to black and white and things of that sort, but all these rich browns and golds and grays, and it's really curious. It's not just that amongst the arboreal fauna that you get all of these different squirrels. You also have this amazing diversity of marsupials. So I made the point earlier when we were talking about the origin of mammals that the marsupials had their origin in North America, made it through Central and South America, and then across the Antarctic into Australia before Australia became isolated. So you ended up with these remnant marsupials in the New World that were then isolated from all the other marsupials. And what's interesting is that the diversity in South America is actually quite extreme. There are probably 35 to 40 different species of marsupials in South America, whereas we only have the one species here in North America. That is a consequence of the faunal interchange that took place across the Panamanian land bridge, or the Central American land bridge. So the Central American land bridge acted as sort of a filter. And of course, when there was this faunal interchange, moving from north to south was a lot easier than moving from south to north because of the habitat differences. And what you end up with is this very distinct, rich kind of fauna in South America and a very different kind of fauna in North America. So we can look at some other morphological changes that have taken place in rodents. And what I want to draw your attention to here is this sort of bizarre convergence in the morphology of the cervical vertebrae. So here you have an example of a jerboa, which is number A, a spring hare, which is in the family Pedididae. It's an African family that contains just the one species. The spring hare looks very much like a rabbit, but it's not. And in fact, it is probably the closest relative to the family Anomaluridae, also the small African family. And then C is a kangaroo rat, so Dipodomys. So you have the jerboa with these fused cervical vertebrae. You have the spring hare with the fused cervical vertebrae. And then you have the kangaroo rat with a fused cervical vertebrae. So these are animals that have essentially no neck mobility, right? And the question is, why do that? Well, the thing that all of these animals have in common is that they're jumping animals. So they use ricochetal locomotion, hopping locomotion, right? And if you're doing that, you don't want your head flopping around all over the place, changing the moments of inertia. So everything is solidified and you don't get any head mobility. Of course, the other group where that happens is in the cetacea, and we'll talk about those guys another time. So here is a skull of Microdipodops, which is the kangaroo mouse. It is a heteromyid rodent. The heteromyid rodents are it's a family of rodents which is adapted to desert conditions or xeric conditions. So there are a couple of cool things that are going on. The one thing that you'll notice is that the rostrum is narrow and long. They actually have a countercurrent exchange system in the nares, not for heat, but instead for moisture, so that the air that they breathe in is very dry. The air that they exhale is also very dry, in spite of the fact that the air has gone down into the lungs. So they're trading the air from the incoming to the outgoing, right? So that rather from the outgoing to the incoming, so that they're conserving all of that moisture. But the most striking thing about this skull is what's going on at the back part of the skull. So you'll notice at the front here, you have the nasals, or you have the premaxilla, then you have the nasals, the frontals, and the parietals. And then there are these bizarre structures, these balloon-like structures at the back. Those balloon-like structures are actually the auditory bullae. So those auditory bullae on your skull, it's just this tiny little button on the base of your skull about the size of your thumbnail or your pinky nail, and that's it. Well, these animals with these large auditory bullae have a sense of hearing, which is just unbelievable. They can hear a snake fart at 1,000 yards, which is important because they're using that hearing in order to evade predators. So not only can they hear the snakes, but they can also hear an owl as it's flying, which is something that you obviously are unable to do. Here's an illustration of of a spring hare, and you can see why people would think of them as rabbits. The difference is obviously that they have longer tails, right? But they do move around by hopping, and as I said before, there's only one species in the genus, the only genus in the family. So it's the family Pedididae. It's South African, and they are presumably the closest evolutionary relatives of the family Anomaluridae. All right, so let's leave the rodents behind for just a moment and consider what's going on with lagomorphs. And as I indicated before, we consider these to be the same essential group. The Russians consider them to be the same. We still keep them divided, but we recognize the fact that there is a close evolutionary affinity between the two. There are a couple of primary differences, though, and you can see those differences by looking at the arrows on this diagram. So if you look at both of them, you'll notice that there are these windows on the side of the rostrum. We say that the rostrum is fenestrated. So the German word for window is Fenster, and here the skull is fenestrated, so it's windowed, right? The other interesting thing is what's going on the right behind the front upper incisors. You'll notice there are these peg-like teeth right behind them. And they're the only group that does that. So they have two upper incisors, one lower incisor. So the peg-like teeth are there, which is kind of odd. There is this other interesting thing that's going on, though, and that is that the lagomorphs are really divided up into two groups themselves. So there are the hares and rabbits in the one group, and then the pikas in the other group. And if you look at the pikas, what you'll notice is that the teeth on the pica are grooved, and that's not something that you see here in these animals. So here, just before we look at the picas, let's compare the skull of a jackrabbit, and then with an Arctic hare. And notice the difference. Notice the incisors, right? How on the jackrabbit, they are more vertical, and on the Arctic hare, they are more procumbent. The other thing to look at is what's going on with the nasal bone. On the jackrabbit, the nasal bone extends pretty far forward, but on the Arctic hare, it's recessed considerably. So you might ask yourself, why is that? Well, I think it's clear, right? The Arctic hare is spending a lot of time chewing through snow and ice and whatnot to get at vegetation. And the jackrabbit clearly is not doing that. There is another interesting thing that morphologically that goes on with jackrabbits, and that has to do with the olecranon process. So look at the illustrations B and C. So in B, you're looking down at the anterior surface of the humerus and then the radius with the ulna right behind it. And notice what's going on as the ulna is extended. there is a small opening at the base of the humerus. So there's a hole at the base of the humerus. And extending from that olecranon process is a little peg. And when that leg is extended, that peg is going to insert itself in that window. So you actually are locking that appendage into place. There's going to be no movement side to side. Very different from your own arm. If you were to extend your arm, it wouldn't be very difficult for somebody to push it against a hard surface and create some significant damage in that elbow joint. That's not going to happen here because the joint is essentially locked into place. Why is that? Well, it makes sense, right? If you are an animal that is changing directions very rapidly. So if you've ever watched a jackrabbit when it runs away from a coyote or away from a fox, it's running in a zigzag pattern. So it's changing direction constantly, always left, right, left, right, left, right. And they do another interesting thing, as you've seen in deer, in white-tailed deer, they flag. So a jackrabbit is going to flag its tail. The undersurface of the tail is white, and it's showing the predator exactly where it is, and it's zigging and zagging left, right, left, right, left, right. Right? Each time planting those front appendages, they're locked into place with that little pin, and then he can exert a lot of energy when he's changing direction. And the tail is flagging up, right, left, right, left, right. And all of a sudden, the jackrabbit will drop the tail and then not change direction. And of course, the coyote or the fox has been following this animal. It's gotten into the habit of looking left, right, left, right, left, right, left, right. And then it looks right, but the animal isn't there because the animal just kept going the opposite direction. So it's kind of a cool predator avoidance strategy that they use. All right, the last animal that I want to talk about is the pika. I had mentioned that within the rabbits there are two groups, right? The leporids. The other group are the ocotonids. So these are the pikas. The image that you see here is a pika. It's a small animal about the size of a guinea pig or so. And you find them in talus slopes out west. So we have one species here in North America, a variety of different subspecies, but they're in the Rockies and in the high Sierras, usually up at a pretty significant elevation. One of the interesting things that they do is they make hay. Well, there are a couple of interesting things that they do. Number one is they practice vigilance, as this animal is doing right here. And they elicit alarm calls, much like squirrels or prairie dogs will do. But they live in these large colonies in these rock piles. They stockpile hay, so they're cutting grass, and they're stockpiling hay in all of these crevices, and that's in preparation for the long winter months. And of course, they have a sufficient quantity of hay so that in the midst of winter, they're going to use the decomposition of that hay to produce heat that will keep them warm, and at the same time they're feeding on the hay as well. And if you look at these guys, what you'll notice is that they have these grooved incisors, as you see here. That's something that you don't find in the leporids. So only the ocotonids have that, only the pikas. Now, for us as biologists, one of the things that is important about pikas is that they are an indicator species for climate change. They are at high elevation. They are constrained by temperature, so they don't have this sort of thermal range that a lot of other animals do. And as the climate changes, as global temperatures increase, they are moving up in elevation. And what's happened is that we've lost a lot of populations of pikas over the last 20 years. So they are used as an indicator species for the health of our global system, I guess. There is this weird population of pikas in southern Idaho. If you're familiar with Yellowstone National Park, you understand that Yellowstone is in what's referred to as the caldera. So it's this sort of crescent of volcanic activity that extends from Yellowstone across that part of Wyoming, across western Wyoming, into southern Idaho, and then into Craters of the Moon National Park, which is sort of a place that not very many people go to. It's an area with a lot of ancient volcanic activity. And so there are these lava flows, and amongst those lava flows, there are pikas, which is sort of an unexpected place for these guys to be. The vegetation around there is pinyon, which is also unexpected because typically you expect spruce or ponderosa or Jefferson pine, something of that sort. But here they are amongst the pinyons. So there's something about the thermal properties of Craters of the Moon National Park which makes it possible for these pikas to hang on. But overall, pikas are not doing well as the climate changes and they're driven higher and higher and higher in elevation. They very rapidly run out of habitat. So while here in the New World, we consider them to be just sort of a biological treasure, it's a different scenario in Asia. In China, in particular, there are efforts to eradicate pikas, and the logic behind that is because they have evil spirits or that sort of stuff. There's a odd sort of relationship with pikas. And other people claim that, which is oftentimes the case, that they're exploiting resources that should be used by sheep or cattle or something of that sort. But it's unclear exactly what the status of pika populations in Asia are. When you go to scientific meetings, oftentimes there will be the occasional Chinese scientist talking about pikas, but it's hard to get a real good feel for what's going on with pikas across Asia. And then finally, if you look at the skull of these guys, you can see that even pikas have that fenestrated rostrum, and they do have those pegged incisors right behind the anterior incisors. So pikas are awesome. If you ever get the opportunity to watch the pikas, it's worth the effort. There are pikas in Grand Teton National Park. If you're ever on your way out to Yellowstone, it's worth the side trip. It's just immediately south of Yellowstone, above Lake Jenny. If you go hike up to Inspiration Point and then continue on past Inspiration Point, there's that valley which extends up pretty high in elevation. It's a hard slog to get up there. But there's a nice large population of pikas up in the rocks. Bring your binoculars because they're very difficult to get close to. They're extremely vigilant. You'll hear them before you see them. You'll hear their vocalizations, their alarm calls as you approach. It is worth the effort, though. All right, that's it for rodents and lagomorphs. Next up will be either cetaceans or carnivores. Talk to you guys later.